Hello, my name is Desmond Edagisi, and I'm here to take us on the subject mathematics. Today, we'll be looking at the topic antilogarithms. Antilogarithms are the inverse functions of logarithms. In our previous class, we learned about logarithm and the logarithm table. Well, the antilogarithm is like an inside-out version of the logarithm, or we could say is the opposite of logarithm. Let's take, for instance, if we have log m given to us as x, and we intend to get our m back, we would simply take the antilogarithm of x to get back our m. So we say m becomes the antilogarithm of x. Let's take a typical example. We have the log of 39.2 to have a value of 1.5933. To get our value 39.2 back, we would simply take the antilogarithm of 1.5933. So the antilogarithm of 1.5933 would give us our value back 39.2. The antilogarithm also comes in a table that is very similar to the logarithm table that we have. But the difference that we will take note of as we go into our class is that while the range of logarithms goes from 10 to 99, the antilogarithm table has a range 0.00 to 0.99. Let's take a look at what the antilogarithm table looks like. So we have our antilogarithm table here. If you do not look closely, you may imagine it to be the logarithm table. They are very similar. But if we look closely, we will see our value range here as 0.00 down to 0.99. The logarithm of a number, when it is given, we can find the number from whence that logarithm number was given back using either of two methods. We can find it directly using the antilog table like we just saw, or we can use a reverse method by looking it up from the logarithm table that we learned earlier about. In our next slide, we'll be looking at how to look it up directly from the antilog table, and further on we'll also look at the other method. Let's go on. Now, we established in our earlier classes that a typical logarithm number, even the antilog number, is divided into our integer part and our mantissa part. We said this division is along the line of our decimal point. So the digits or the numbers we have before the decimal point are referred to as the integers, while that after our mantissa point, of course the fractional part, are referred to as the mantissa. Now, to find the antilogarithm of a given log number, the integer part, which is also known as the characteristic, is determined by the value that is within our log number. Take, for instance, this number here. The value of our integer in this part is 0. To find the integral part of the antilog of this, we simply add 1. So we add 1 to whatever our value is in our given log number. Let's take a look at this example. We have the given log number as 0.4362. The integer part of our antilog here would be 0 plus 1, which would give us 1. This one, we must please take very good note of, is not a value of itself, but an indicator of the number of digits within our answer that we would have before a decimal point. Let's take this example so we understand. Now we're given this log number to find the antilog of this number, 0.4362. The antilog of 0.4362 is 273 as a value. This integer part that we calculated to be 1, like we said, indicates the number of digits we have before a decimal point. It means that within this number string we would have 1 digit before our decimal point, and that first digit here is 2, so we move ones, and hence we have 2.73 as we have here. We are not taking things this fast. We're going to learn how to actually find our antilog numbers, but here we just want to explain to you how we first find our integral part, and then later on we'll see how we can find our mantissa part. Let's take a look at another example. If we were given this number 1.4362 to find the antilog of 1.4362. Now first we'll find our integral part. To find our integral part, we said earlier that we simply add 1 to the value of our integer in our original number. So we have 1 as our number, we add 1, and hence we have 2. But also we said that the number we get, which is 2 in this case, is not a value of itself, but only an indicator of the number of digits we would have in our final answer before a decimal point. So if the antilog of 1.4362 would give us a number string of 273, our value 2 here, which we calculated as our integral part, indicates that there are 2 digits before the decimal point. So we would have our digits move, our decimal point move once, twice, to give us 27.3. I hope it's getting clear. Let's take a look at yet another example. If we were asked to find the antilog of 2.4362, again, to find our integral part, we said we'll add 1 to whatever the value of our integer in the given number is. Here we have 2, so if we add 1, we would have 3. 2 plus 1 is 3. This 3 again, we said, is not a value of itself, but an indicator of the number of digits that we would have in our final answer before the decimal point. So if we use our antilogarithm table to find the antilogarithm of our mantissa part, which is 0.4362, we'd have a number string of 273. In this number string, we said we have our integral value as 3, indicating 3 digits before our decimal point. So if we move our decimal point here, we'll have 2 times, 3 times, and that would be 273.0, which of course is still 273. Now we know how to find the integral part of our antilogarithms. After now, we'll see how to find the mantissa part of our antilogarithms. Let's go further. Now we've established that the typical number given for us to look up the antilogarithm is divided into its integer and the fractional part. We've also found out how we can find the integer. Now we're going to see how to find the fractional part. The fractional part of a given log number is simply looked up from the antilogarithm table. We said the antilogarithm table is very similar to our logarithm table. So just like the logarithm table, it has rows and columns. These rows, on the other hand, different from what we have in the logarithm table, ranges from 0.00 to 0.99, while the logarithm table, like we said, ranges from 10 to 99. And of course, these values also have the mantissa part of our antilogarithms within. Just also like the logarithm table, the first 2 digits of our given number is looked up from our rows. Let's take a look at a typical antilogarithm table. So once again, we see the similarity the arrangement of our table very similar, but our values of our rows, the ranges are different. So we have ranges from 0.00 to 0.01 to 0.02 down to 0.99. So we said if we have a string of numbers to look up, the first two digits of our number, just like the logarithm table, is looked up from our rows. We also have columns within that logarithm table, as we saw. The column intercepts the mantissa part of our antilog of our given number. And the third digit, if we have a number string that has a third digit, that third digit is looked up from our column within the antilog table. The other column, which is named difference within the antilog table, is used to trace the last digit. If we have a last digit, so if we have 4 digits, we say the first 2 digits are traced from the row. The next digit, which is the third digit, is traced from the normal column, while our last digit is traced from the difference column. Let's take a look again at a typical anti-logarithm table. So we've established that the first 2 digits of our number is traced on our row. If we have a third digit, it is traced on this column. Like we can see, our columns are labeled, so depending on our number, we look up our third digit number here to trace down to intercept our rows. If we have a last digit, we look it up on this section of our column known as the differences. Now the numbers or the values we get from the row, the column, the difference, they are added up to form the mantissa of any given logarithm number. Let's take this typical example. If you've been asked to find the anti-logarithm of 0.4362. 0.4362. Once again, we said a typical anti-logarithm number is divided into its integer and the mantissa. So to find the integral part, remember, we said whatever our value is here, we add 1 to it. So we have 1 as our value. But we said this 1 is not a value of itself, but an indicator of the number of digits within our final answer that would appear before a decimal point. So let's keep this somewhere, while we go ahead to find the mantissa part, which in this case is 0.4362. The mantissa part, we said, is looked up simply from our anti-logarithm table. Let's go ahead and look at our table. So we have our row here as 0.43. If we trace this down, the third digit 6 would be traced on our column here, traced down to get an intercept of 2729. While we have a last digit 2, we said the last digit, which is the fourth digit, is normally traced on the differences column. So if we trace that down to intercept our row, which is 0.43 here, we have a difference of 1. So we add up our two values, 2729 and 1, to get 2730. 2730 here is our number string gotten from the antilog table. But remember, we have our integral part, which we calculated to be 1 here, that indicates the number of digits we have before the decimal point in our final answer. If this is our final answer, 2730, therefore this 1 indicates that we'll have 1 digit, which means our decimal point moves 1 step and would have 2.730. This is the anti-logarithm of our number here, 0.4362. Now we know how to find the anti-logarithm of a number, making use of our logarithm table. Remember, we said there are two methods. So now we're going to look at the second method. We said we can instead use the reverse method by making use of still the logarithm table to do a trace back to get the original number from whence a logarithm number was obtained. To do this, we follow three simple steps. First, we search for the number directly or any number closest to it in our logarithm table under the rows and columns. Next, we do a search in our difference column to get a number, as the case may be, that makes up the difference when it is added to our log number. And finally, we trace our number on the row, column, and difference to get the original number. I guess this may seem strange, but as we do a practical example to look directly on our logarithm table, we'll understand better. Now, if we were asked to find the anti-logarithm of 0.6763, find the anti-logarithm of 0.6763. Remember, we said our logarithm table contains only the mantissa part of a number that we seek, while our integer part is calculated in a different manner. So once again, to find anti-logarithms, to find the integer part of anti-logarithms, we said whatever value we have in our given number, we add 1 to it. So here we would have 0 plus 1 to give us 1. And we said this 1 is an indication of the number of digits again that would appear before the decimal point in our final answer. So let's keep this aside and look for the mantissa part using the logarithm table instead of our anti-logarithm table. Now, we said we do a search. We generally look up our numbers here under the rows and column. We have numbers. If we notice, the numbers increase progressively. So if we have 7152 here as a number, it means that the number we seek, which is 0.6763, would be somewhere higher. So we just scan through to get, if we're lucky, we can get a number directly or something close to it. In this instance, we have 6740 here. 67, sorry. In this instance, we have 6758, which is close to 6763. The next number is higher, 6767. So it means that this is the closest number to which we can have. If we simply circled it, 6753. But it is less than the number given to us. So we do a subtraction. What is the difference between 6763 and 6758, which is closest? The difference is 5. And that is where we look up the value 5 under our difference column. So we know why it is called a difference column. The difference between the closest number we got to our given number is 5. And we look it up here. Still on this row that we've established our closest value is. And now we have our values here. We trace it up. If we traced here, we'd get the difference value as 5. If we do a trace up here too, we get our third digit as 4. And if we do a trace on our row here, we'd have 47 as our number. If we add up our numbers on the row, original column, and difference column, we would have our string of numbers. Let's do that quickly. So we have 47 as our first two digits, the next digit being 4, and our final digit as 5. This is our number string. But once again, remember we calculated the integer part to be 1, which again we said is an indication of the number of digits before our decimal point. So our decimal point will move once, and this would give us 4.745. This is the anti-logarithm of 0.6763. Very simple. Let's take a look at a much simpler situation. If we were asked to find the anti-logarithm of 1.5933, once again, quickly, to get the integral part of our anti-logarithm, we said we'd add 1 to whatever value that we have on our given number. So if we added 1 to 1 here, we'd have 2. 1 plus 1 would give us 2. We said this 2 is not a value of itself, but an indicator of the number of digits in our final answer that we would have before a decimal point. So let's keep this as an aside and go ahead to find our number, our mantissa part of our string here. So we do a search of 0.5933 on our logarithm table. Wow, we have a hit. We have a direct hit over here as 5933. So this is a much simpler situation from what we did earlier. So once we have this, we have no need to look for differences. We just do a trace up to get our third digit as 2. We do a trace horizontally along our row to get our first 2 digits as 39. So we have a number string of 392. Applying the integral parts of what we determined earlier, 2 digits before the decimal point, we'll move our decimal point once, twice, to get 39.2. And this is the anti-logarithm of 1.5933. That's the second method we can use in finding the anti-logarithms of our given logarithm numbers. So far, we've learned about anti-logarithms. We learned that they are the inverse functions of logarithms, or in other words, they are the opposite of logarithms. We said, for instance, that if we have the log of m given as x, to get our value m back, we'll simply take the anti-logarithm of x to get back our m. So m becomes the anti-logarithm of x. We said the anti-logarithm table is very similar to the logarithm table. The only difference that we notice is in the range of its value. We said while the logarithm table ranges from 10 to 99, the anti-logarithm table ranges from 0.00 to 0.99. Also, we said the anti-logarithm table is similar to the logarithm table in that it is broken in 3 parts. We have our rows, the rows of our numbers, of course the range 0.00 to 0.99. Then we have the normal column and a special column which is called the difference. Just like the logarithm table, we said all of this is combined to help find the anti-logarithm of numbers. I'm sure you've learned a lot so far. It's been a pleasure for me taking you on this class, and I look forward to seeing you in our next class. For me, it's bye for now.